Hello, AP Chemers. Topic is acid-base equilibria. So, equilibrium systems where you have acid and base reactions. We had already talked about the Bronsted-Lowry acid-base definition. We said that an acid is a proton donor, a base is a proton acceptor. Every acid has a conjugate base. Every base has a conjugate acid. The strength of the acid tells you the strength of the conjugate base and vice versa. And so we have a list right here of some different acids. So here's the acid, here's its conjugate base, or you can think about it as this is a base and this is its conjugate acid. So as you can tell, as my acid strength increases, my conjugate base strength decreases. So the stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. Now let's say I have these reactions and I want to know which way the equilibrium will lie. Would it be towards the right, towards the product, so it's product favored at equilibrium, or is it towards the left, where it is reactant favored towards, at equilibrium? So first let's label our acids and bases here. So let's see, I have HSO4 minus, so that's an acid. NH3 is a base. NH4 plus is the conjugate of the base, so this must be my conjugate acid. And then the SO4 minus is the conjugate of my acid, so that is my conjugate base. So to determine which way the equilibrium lies, what you want to do is compare your acid with the conjugate acid and the base with the conjugate base. Figure out which is the strongest acid, which one is the stronger base. And the equilibrium will lie towards the weaker species. So let's start with our acids. So I have HSO4 minus versus NH4 plus. And we want to find those. So here's my NH4 plus. And here's my HSO4 minus. It looks like my HSO4 minus is the stronger acid. So I'm going to say this is stronger. All right. I'm going to look at my base. So I have NH3 and SO4 minus. Those are my two bases. So I'm going to find those on the bases. So NH3 is right here. And then SO4 minus is right there. It looks like NH3 is my stronger base. And so my reactants are stronger acids and bases. The equilibrium will never go to anything strong or anything reactive. If they're strong acids and bases, that means they will dissociate, they will react, they won't stay the way that they are. Equilibrium will always lie towards the stable, weaker species. And so that means that my equilibrium in this case will lie towards the right, favoring the weaker species. Let's look at the next one. So the next one, I have HCO3 minus reacting with HS minus. Now it's hard to tell which one's the acid, which one's the base in this one. So what you want to do is start with one of them, HCO3 minus, and look at its conjugate. Looks like CO3 minus is its conjugate. They look very similar, right? The HCO3 minus lost a proton, so that tells you that that was your acid, and this would be your conjugate base. So let's label those. It's my acid. This is my conjugate base. This then must mean that's my base, and just to check, this is my conjugate acid because both of these look similar, except that this has an extra H+. The base accepted a proton to become the product. So let's compare my acids and bases again. So I'm going to, let's try the acids first. So I'm going to look at my HCO3 minus versus my H2S. Let's see if we can find those. there's my H2S and HCO3 minus. So it looks like my H2S is stronger. Now I'm going to look at my bases. So I have HS minus, CO3 2 minus. There's my HS minus. There's my CO3 2 minus. Looks like the CO3 2 minus is my stronger base. And so in this case, the equilibrium will lie towards the left, going towards the weaker species again. Now we have not only just looked at comparing acids and bases, but we also actually calculated pH values and POH values. But all the ones that we've done so far were for strong acids and bases. If you have a strong acid or base, you know that it completely dissociates, and so you can calculate the pH and the POH just by using the molar concentrations. For example, let's say I have HCl. I know that it's going to go 100% to H plus and Cl minus. So if this is 1 molar, for example, this would also be 1 molar, and this is 1 molar. So I already have my H plus concentration, and I can calculate my pH very easily. But let's say now that you have a weak acid like HF. That does not go 100%. In fact, very little of it actually dissociates into H plus and F minus. And so if this is 1 molar, I don't know what these are. I know they're less than 1 molar, but I don't know what they are. So if you have weak acids and bases, you have an equilibrium going on here, and so you have to use equilibrium calculations, which means ice charts. So let's try some examples. Let's start with the first one here. It says lactic acid. They give you the formula. They give you dissociation as well. It says it has a pH of 2.43 when 1/10 of a mole is dissolved in 1 liter of water. What is its acid dissociation equilibrium constant? Now that's a long name. Acid dissociation equilibrium constant. What's that? That's just the Ka. That's all they're looking for is Ka. So we're going to start with the dissociation equation. We're given that. I'm just going to rewrite it in case I need an ice chart or something. You're welcome to rewrite it as this, and normally I would. But I also want to show you that, let's say you're on the test, you're in a hurry. You can abbreviate stuff if you wanted to. So you can write it as, for example, since it's called lactic acid, it's found in milk. Maybe I would call it HLAC. And it would dissociate into H plus and then lactate ion. You can write it that way if you want. It's up to you. As long as I'm not asking for any formulas or equations or something like that, it's okay to abbreviate stuff like this. Now I want the Ka, so I'll write the Ka expression. It's going to be equal to the H plus concentration times the lactate ion concentration over the concentration of my acid, lactic acid. And I don't have any of these numbers, so maybe I should start an ice chart, so I'll do that. And originally I know that I have 1/10 of a mole in 1 liter of lactic acid, so that ends up being 1/10 molar. I know I start with these as zeros. And I know that some of it dissociates. I don't know how much. However, I am given another number. I'm not given the K, but I am given a pH. Now, what is the pH related to? It's related to the H plus concentration at equilibrium. So if I have the pH, that means I have the H plus concentration at equilibrium. The pH is, the H plus concentration is equal to 10 to the negative pH. So it's 10 to the negative 2.43, which is 0.0037 molar. So I just got the concentration of the H plus at equilibrium. So I'm going to go back to my ice chart and put that number in, 0.0037 molar. And if I know what it started with, which is 0, and I know at equilibrium, then I know what the change is. The change is that it gained 0.0037 molar. And if I know the change for one of them, I know the change for all of them. This would be plus 0.0037 molar, and this would be minus 0.0037 molar, because they're all a 1-to-1-to-1 ratio. And so this is 0.0037 molar, and this one is 0.0963. Now I actually have my equilibrium concentrations. I can plug those into my Ka expression. So my Ka is going to be 0.0037 molar times 0.0037 molar over 0.0963, which gives me a Ka of 1.42 times 10 to the negative 4th. And that's my answer. Let's try another one. Number 2 says I have 0.02 moles of benzoic acid. It's added to 1 liter of solution. And I want to calculate its pH, but I'm given the Ka this time. So it's kind of the opposite of the last one. Now they give me what benzoic acid looks like, and it kind of looks a little intimidating. Don't let that scare you. It doesn't really matter. It's an organic acid. There's my H that leaves off, and it's given to the water. So you get hydronium ion, and then there's your benzoate ion that's left. If you don't like this, rewrite it. You know, you could always say this is H-benz, for example, plus water yields benzoate ion plus H3O plus. If you don't even like that, if that's too much, you could just ignore the water and write H plus. It doesn't really matter. Again, as long as you're not asked for, the K expression or the dissociation equation or something like that, it doesn't matter. You can abbreviate it for yourself. So let's try to do this. I'm given the Ka, and I'm trying to find the pH. Now the pH is going to be my H plus concentration at equilibrium. So it looks like we need an ice chart here. So let's start an ice chart. I know that I have 0.02 moles in 1 liter, so this is 0.02 molar initially. I don't care about the water, it's a liquid. It's not part of my equilibrium. I start out with 0 and 0 for my products. The only other number I'm given is the Ka, so it looks like I need some x's there. So this is minus x, and plus x, since they're all a 1-to-1. So 0.02 minus x, and x. And let's write out our Ka expression then. So our Ka expression is going to be the concentration of the benzoate ion times the concentration of the H plus or the H3O plus, whatever you want to call it, over the concentration of my benzoic acid. So my Ka is given to me. It is 6.3 times 10 to the negative 5th. That is equal to x times x over 0.02 minus x. If you solve for x, that's going to give you your H plus concentration at equilibrium, or H3O plus. And for that one, I got 0.0011 molar. So if I want the pH, it's going to be the negative log of 0.0011, which ends up being 2.96. And that's my answer. Let's try another one. I want to calculate the pH of a 1 molar solution of HF. I'm given the Ka for it. I also want to calculate the percent dissociation. What percentage of it turned into ions? So I'll start with my dissociation equation. That one's pretty easy. I don't need to abbreviate it. So HF partially dissociates into H plus and F minus. I'm given the Ka, so probably a good idea to write the Ka expression. H plus concentration times the F minus concentration over the HF concentration. And I know that this is 7.2 times 10 to the negative fourth. I don't know much else. The only thing else that I'm given is the initial concentration. So it looks like this needs an ice chart. So initially, this is 1 molar, 0 and 0. Since I don't have any other numbers other than the Ka, I'm going to use x's. So minus x plus x plus x. 1 minus x, x, and x. So my 7.2 times 10 to the negative fourth, that's my Ka, that's equal to x times x over 1 minus x. If you solve for x in this case, that's my H plus concentration at equilibrium. And when I calculated that, I got 0.0268 molar. So if I want the pH, it's going to be negative log of 0.0268, which is 1.57. I also wanted to calculate the percent dissociation or percent ionization, same thing. So that's how much of it dissociated divided by the total times 100%. Percent dissociation would be the amount that dissociated divided by total times 100%. Let's see if I have these values. How much dissociated? Well, how much dissociated would be my x. And so I figured out what x is. It's 0.0268 molar. Divided by the total, that was my total. So 1 molar times 100%. And so that's 2.68% dissociated. Think about that. That's a small number. So we're saying that for every 100 HF molecules, not even 3 of them dissociate into the ions. So more than 97% of the HF molecules remain molecular. They do not ionize. So very, very little ionization. And compared to weak acids, HF is one of the stronger weak acids, you know. That Ka is relatively large for weak acids. So, you know, most acids do very, very little ionization. All right, let's say that you have a mixture of different acids and you want to try to figure out what the pH is. Now, in this mixture, we have some HCN and some HNO2, both relatively weak acids. Actually, both weak acids. So let's say that you have strong acids, 2 strong acids. Let's say you have some HCl and some HBr, for example. You mix them together, you want the pH. Well, the correct way of doing it would be to, since they dissociate 100%, you want to figure out how many moles of H plus are produced from the HCl, how many moles of H plus are produced from the HBr, add them together. That's going to give you the total moles of H plus, and from there get the pH. So for weak acids, you would probably want to do the same. So some of this dissociates to give H pluses, some of this also dissociates to give H pluses. You want to figure out how much H pluses you get from both and then add them together and that would give you how much the total of H pluses, right, to get the pH. Well, let's look at their Ka values. Now, they give you the HCN, they give you the HNO2. They, just for fun, also they give you the water dissociation constant because, well, some of that water dissociates and gives off H pluses as well. But look at that number compared to these. That's a pretty small number. Now this, just to show you, the numbers compared to each other, this is 0.0004, right? Now let's look at the top number. That's 0.00000000062. This one, 0.0000000000001. Look at those numbers relative to each other. I mean, the top one and the bottom one are negligible compared to this. That's such a huge number compared to these two. So if I were doing this problem, you're welcome to figure out how much H pluses you get from all three of them, or at least from those two and add them together. I personally would not do that. If I figure out how many H pluses are from here and then from here and I add them together, it's still going to equal this number with sig figs. This is going to be very, very, very minimal H pluses compared to that. And so to be honest with you, if I were to do this, I would only focus on this one right here. So I would say this is the only significant source of H pluses. I would say that both of these are negligible because their Kas are so small, which tells me very, very, very little of them ionize and turned into H pluses, that I could ignore them. So I'm just going to do the HNO2. So HNO2 dissociates to give off H plus and NO2 minus. Let's do an ice chart. This is 5 molar, 0 and 0, minus X, plus X, plus X, 5 minus X, X, and X. My Ka is going to be the concentration of H plus times the concentration of the NO2 minus over the concentration of the HNO2. And so 4 times 10 to the negative 4th is equal to X times X over 5 minus X. If you solve for X, and again, that's your H plus concentration at equilibrium, that's your X. That turns out to be 0.0445 molar. And so your pH is going to be negative log of that, which ends up being 1.351. If you were to actually calculate how many H pluses come out from here, it's probably going to be, like something times 10 to the negative 6th or something like that. And so when you add it to this, you're still going to get 0.0445. So the pH would be the same. Now, what if I want to calculate the percent dissociation of HNO2? We just did it in the previous problem, so you would say percent dissociation is going to be how much associated, which is my X, which in this case is 0.0445 molar, divided by my initial, which is 5 molar times 100%. That doesn't even give you 1%. That gives you like 0.89%. That is so small. And yet, it was the strongest by far of those. This is telling you that more than 99% of it stays as molecular HNO2. Less than 1% turns into H plus and NO2 minus. Let's try another one. It says a certain weak acid, HA, is dissociated 0.003%, very little dissociation, in a 1 molar solution. Calculate, that should say, its acid dissociation constant. So we want to calculate Ka. I start with my dissociation equation. Since I'm not given what the acid is, I'll just use HA, H plus and A minus. Since I want Ka, I'll write the expression. It's the concentration of the H plus times the concentration of the A minus over the concentration of HA. And let's start an ice chart here. We know that this is 1 molar, 0 and 0. Now I am given another number. It's not my Ka, it's not my pH, it's the percent dissociation. So it's telling me that 0.003% of it dissociated. So this is actually my change. That's like my X, right? But that's the percentage. You got to change it to decimal. And so it's really 0.00003 times the 1 molar, which is 0.00003, right? Because that's percentage. You got to change it to decimal, so you divide by 100. So the change for this one is minus 0.00003, which tells me the change for this one is plus 0.00003, and this one is plus 0.00003. So at equilibrium, this one is 0.99997, 0.00003. It's a lot of zeros. 0.00003. So my Ka is going to be equal to 0.00003 times 0.00003 divided by 0.99997. Let's see if you can do this without a calculator. You can do this. Here we go. This is about 1, right? 0.9997. I mean, that's pretty much 1. So let's say that that's 1. Okay? The top number here, that's 4 zeros, so this is 3 times 10 to the negative 5th. And then this is also 3 times 10 to the negative 5th. Let's see, 3 times 3 is 9. 10 to the negative 5th times 10 to the negative 5th is 10 to the negative 10th. Divided by 1 is itself. So 9 times 10 to the negative 10th. See, you can do mental math. All right, let's try this one. Polyprotic acids. What does polyprotic mean? Well, poly means many, protic means protons. Acid means something that gives off H pluses or protons. And so these are acids that have multiple H pluses to give off. Now, always, the first proton that's given off is way stronger than the second one. We see that with H2SO4 because we know that the first proton goes 100%, dissociates 100%, but the second one only partially dissociates, and there's its Ka there. And this is true for all different acids like, let's look at phosphoric, for example. Look at the Kas. This is for the first hydrogen, 10 to the negative 3rd. The second one, 10 to the negative 8th. Third one, 10 to the negative 13th. Big difference here. So the first hydrogen is always much stronger than the second one, which is much stronger than the third one, and so on. So let's say I want to calculate the pH of H2S. H2S is diprotic. Here are my Ka1 and Ka2. This is for the first hydrogen, this is for the second. I know that it dissolves to an extent of 10th molar, so I have a 10th molar solution. I want to know what is the pH, and I want to know what are the concentrations of all the different species at equilibrium. So I'm going to start with writing the dissociation equations here. So I have H2S dissociating into H plus and HS minus. And then my HS minus can further dissociate into H plus and S2 minus. So let's start with the first dissociation here. I'm going to start with an ice chart. I know that my H2S is 10th molar initially, 0 and 0. I only have the Ka, so I'm going to use X's for the change. So minus X plus X and plus X. So this is 0.1 minus X, X, and X. So I'm going to say Ka1 is equal to the concentration of the H plus times the concentration of the HS minus over the concentration of the H2S. And that's, again, after just the first dissociation there. So 1.0 times 10 to the negative 7th is equal to X times X over 0.1 minus X. X in this case is going to be my H plus concentration. Now this is only after the first hydrogen. It's also going to be my HS minus after the first dissociation. And I got that to be 0.0001. So now, after that dissociation, some of that HS minus is going to dissociate to turn into H plus and S2 minus. So I'm going to make a new ice chart for this one. And my HS minus starts out as 0.0001 molar. I got that from here. And I don't have any S2 minus to start with, but I do have some H pluses, right? Because after the first dissociation, I got some H pluses. So this is also 0.0001 molar. Now, some of that is lost. So minus X, and just so we don't get confused, I'm going to say Y instead of X. So minus Y plus Y plus Y. So 0.0001 minus Y, 0.0001 plus Y, and Y. So Ka2 is going to be the concentration of the H plus times the concentration of the S2 minus over the concentration of the HS minus. And my Ka2 was 1.3 times 10 to the negative 13. It is equal to 0.0001 plus Y times Y over 0.0001 minus Y. Now, to be honest with you, if I were doing this, if you compare this value, negative 13th, with this, which is negative 4th, this is negligible. So the dissociation is negligible, basically. Like, very little of it will dissociate. And so Y is very, very small, is what I'm saying. And so you can ignore that Y and that Y. And so it's 0.001 times Y over 0.001. Those can cancel. You'd end up with Y is equal to that Ka2. Now, if you don't want to do that, you want to be on the safe side, you're welcome to punch it into your calculator. If you go ahead and do that, you will get that Y is indeed 1.3 times 10 to the negative 13th molar. So now I can actually answer my question. It asked for the pH. So the pH, well, let's wait for the pH for a second. Let's do the other things it asked for. Let's do the concentrations first. So let's start with the H2S concentration at equilibrium. The H2S dissociated, and at equilibrium is 0.1 minus X. So that's sorry, my stylus is acting up again. 0.1 minus 0.0001, which is basically 0.1 molar. I mean, if you want to say 0.999, that's fine. But it's close enough to 0.1 molar. All right, next, let's do the H pluses. So the H pluses were X after the first dissociation, but then that X, we added to it. So now at the new equilibrium, it's 0.0001 plus Y. So 0.0001 plus 1.3 times 10 to the negative 13th, which is 0.0001 molar. Let's look at the HS minus. After my second equilibrium, it's 0.0001 minus Y, which is 0.0001 minus 1.0 times 10 to the negative 13th, which is also 0.0001 molar. And then S2 minus, at equilibrium it's equal to Y, so it is 1.3 times 10 to the negative 13th molar. Finally, my pH is negative log of the H plus. We got the H plus to be right here. Oops, sorry, right there. 0.0001, which is pH of 4. Now I want you to take, it's really long, I want you to take a look at our answers here. So our concentrations, these, and then our pH. Which of these could we have just answered from the first ice chart? Let's look. H2S, 0.1 minus X. Yep, I could have answered that. H plus, I ended up with 0.0001 molar. Look, I ended up with 0.001 molar. HS minus, I ended up with 0.001 molar. 0.0001 molar. All match. S2 minus, ooh, that one I needed the second ice chart for. pH is negative log of the H plus, so I could have gotten all of these from the first one, except for the S2 minus, except for that second anion. In addition, though, look at the concentration of the second anion. The second ionization is so small that the concentration of this is usually what the Ka2 is. So really, if you're on the test, I would probably answer these questions just based on the first ice chart. I wouldn't do two of them. I would say second ionization is too small, too negligible, and I would come up with all the answers just based on the first ice chart. By the way, that second ice chart would never be asked on the AP exam. I could ask for it on my test or my worksheets, but again, you really can just do this, but it will never be asked on the AP exam. They would maximum ask you for one ice chart, never two. So far we've been talking about acids and doing all the calculations with acids. We haven't really done any examples of bases, so let's do a few. A base, remember, is a substance that accepts a proton. So B is our generic base, it's not boron. So there's our base, reacts with water, grabs an H plus from it to become the protonated form of it, which is BH plus. And then you have OH minuses, and that raises the hydroxide ion, drops the H plus ion, and therefore your pH increases. A lot of bases have some bases have hydroxides in them, but a lot of bases are molecular, not salts, not hydroxide salts. And so a lot of them, you'll notice, will have a nitrogen with a lone pair. Like, for example, ammonia is NH3. Looks like this, where you have a lone pair on that nitrogen. Methylamine looks like this. Dimethylamine looks like this. Pyridine looks like this, and so on. I'm not going to draw nicotine and caffeine, they're kind of long, but you get the idea. You have this lone pair typically on the nitrogen. That is what allows it to grab an H+. Let's try an example here. It says pyridine, a common weak base, has an ionization constant of 1.5 times 10 to the negative ninth. Let's say you dissolve 0.01 moles of it in 1 liter. What is the pH? And then also, what is the Ka of its conjugate acid? So if it's an acid, we have a Ka. If it's a base, we have a Kb. And so when it gives you an ionization constant, if it's a base, then that means that this is your Kb. So let's try it here. Let's first write, well, actually they wrote for us the dissociation equation there, so no need to do that. So since it's an equilibrium, I'm going to go ahead and start with an ice chart. Initially I have 0.01 moles in a liter, so this is 0.01 molar. I don't care about the water, it's a liquid. 0 and 0. Let's see if I'm given any other numbers. The only other number is my Kb. Let me set up my Kb expression. It's going to be the OH minus concentration times the protonated form of the pyridine over the pyridine. And again, Py is an abbreviation. Just like we abbreviated our acids like benzoic acid and lactic acid, you can abbreviate your bases as well. It doesn't really matter. Since I'm not given any other numbers, I'm going to use x's. So minus x plus x plus x, 0.01 minus x, x, and x. And so 1.5 times 10 to the negative ninth is equal to x times x over 0.01 minus x. My x in this case is actually my OH minus concentration, not my H plus. This is my OH minus, and so that ends up being 3.87 times 10 to the negative 6 molar. And so I have to find my POH first. POH is going to be negative log of that, which is 5.41. So my pH is 14 minus that. It is 8.59. It's 9 there. Now I also want the Ka for the conjugate acid. By the way, what is the conjugate acid for this? This is your base. Here's your conjugate acid, the PYH+, the protonated form of it. So whatever the base is, just add an H plus to it. That's going to be your conjugate acid. So for any acid and its conjugate base, or base and its conjugate acid, here's an equation that's useful. Ka times Kb will always equal to Kw. So let's use that. So my Ka is equal to Kw over Kb. So 1.00 times 10 to the negative 14 over 1.5 times 10 to the negative 9th. And that ends up being 6.7 times 10 to the negative 6. All right, that's it for today. Hope you have a great and wonderful rest of your day. See you in class soon.